Hi everybody, I'm Leonardo Araque and I've created this video to help you with homework number 3. So I will go over the main points of the finite element method applied to the homework. Okay, so the first step is determine the ODE for the physics of the problem. This step was already done, is given in the statement, in the problem statement, right? And the second the third step, according to our procedure, is to derive the weak form of the problem. Since we've already done this for the previous homework, I'm gonna go straight to the formulation of the weak form. So the weak form for this specific problem was derived in homework number 2. And it should look like this form, where we have the conductivity term, the area, the cross-section area for the fin, the derivatives of the function t, and the wave function v prime, the perimeter, the convection term, T infinite accounts for the ambient temperature, room temperature, and the last term corresponds to the boundary conditions. I think I missed the K here. Okay, so the first, or let's say the third step in our finite element procedure is to derive apply this weak form for an element. So let's do that. So the weak form for an element, the limits of integration goes from xi to xj. And we have pretty much the same integrand. And our boundary conditions will be evaluated between xi and xj. All right, so once we set our weak form for an element, for a general element, the next step would be to set the approximate function. Okay, so the approximate function for this case. So this is the weak form of the problem. Now the approximate function. So the approximate function for this problem for a general element should look like this, where Ti is the constant we're solving for, and Nix represents the shape function at node I. Similarly, we have a shape function attached to a constant tk, a node k, and the same applies for the node j. This dot product between the two vectors will give me the same result. So it means that I can write it down in vector form in the following way. Where the underscore, the underline means vector. So here, the shape functions for a quadratic formulation look like this. All right. So next step is to define the derivative of the approximate function. So for the derivative for the element, for the approximate function for each element, we're taking the derivative of the shape functions because are the only components in this expression as a function of x. So if we take the derivatives with respect to x for each of the shape functions, we should be able to express the derivative of the approximate function. So this this vector b represents the derivatives of the shape functions, and that's what we're gonna. That's what this term will be seen later in the reformulation of the weak form for the element. All right. So now that we defined approximate functions and its the approximate function and its derivative, we can proceed to reformulate the weak form for the element. So the weak form for the element as a function of the approximate functions and the shape functions between the limits xi to xj has the general form of the product between the transpose of b times b times the vector containing the unknown coefficients t. And this lowercase q represents a, I'm missing something here, sorry. Because all of this is inside the integrand. And this lowercase q, this vector lowercase q, represents the boundary conditions at each node of the element. Okay, so if we rearrange terms in this new formulation for the weak form, I will leave the components of the stiffness matrix on the left-hand side and the components of the force vector on the right-hand side of the equation. And remember that you cannot pull out the terms for k and p from the integration because they are also a function of x. So they are not constant terms in this case. So you cannot do that. Okay, so this is B transpose B, N transpose and N are vectors, right? Ti, the vector T containing the unknown coefficients and on the other side we have the forcing vector, the force vector. And the vector lowercase q representing the boundary conditions in this problem. So you can see that on the left-hand side, all these integral belongs to the stiffness matrix for the element. And on the left-hand side, all these terms belong to the force vector. All right. So now for our element with 3 nodes, nodes I, K, J. This is for the general element. We need to be more specific in our problem. So our discretization is with 2 elements. So we need to apply for each of the, we need to apply this weak form for a general element to each of the elements in our discretization. So it means that we have 2 elements. This is element 1 with nodes x1, nodes at x1, x2, and x3. And our second element connected with our second element at nodes x4 and x5. So x3 is repeated, right? It's a common node between the 2 elements. Okay, so saying this, our weak form for the first element is defined between the limits x1 and x3. The stiffness matrix with the components for the first element is a 3 by 3 matrix. The vector with the unknown coefficients are T1. The components for the vector with the unknown coefficients are T1, T2, and T3. And the fourth vector for the first element contain the boundary conditions for the nodes 1 and 3. Right? Because our boundary conditions for each element are defined only at nodes I and J, the end nodes of the element. So in the middle, we don't have any boundary condition. Now, for element 2, the limits of integration are from x3 to x5. We have the same size for the stiffness matrix. And the components with the unknown coefficients are T3, T4, and T5. And the fourth vector for the second element contains a term with the boundary conditions with components, whose components are Q3, 0, and Q5. All right. Okay, so it means that Our stiffness matrix for the first element is a 3x3 matrix. And the degrees of freedom for this are, let's say the nodes associated with this stiffness matrix are node 1, node 3, node 2, node 3, node 1, node 2, node 3. For K2, we have a similar case. But the nodes are 3, 4, 5. 3, 4, 5. And we use this code, this table code, to generate the assembly, the big K, the big stiffness matrix, the assembly stiffness matrix, which contains the information for the stiffness matrices from each element. Okay, so if we assemble these two matrices, we'll end up with a matrix 6 by 6. Okay? Similar procedure is done for the force vector. So it means that the force vector should be a vector 6 by 1. Okay? And this takes us to the system of algebraic equations, which in matrix form should look like KT, where T is also a vector 6 by 1 equal F. All right? So now this is the time, this is the moment where we impose the boundary conditions. So if you follow this procedure, I didn't impose the boundary conditions at the beginning. I just leave it like a general case. And this is what we actually do. So now I can go to the force vector, and at the corresponding node or degree of freedom, I can impose the boundary condition if there is any. All right? Which is for the last node in our element, which is at the position x5, we have a natural boundary condition. So we need to make the substitution on that forcing vector at that node, all right, for that boundary condition. And we have an essential boundary condition at the node x1, right? In the position x1. So we need to go to with the vector t and make the corresponding substitution. We impose that boundary condition in that vector in the corresponding location. All right? And then we proceed to solve this system of algebraic equations. So I'm going to say that this is the moment right before solving the system of algebraic equation is the right moment to impose the boundary conditions in our system of equations. Okay? So that's what we need to do. That's what we need to do to solve this problem. All right, now if we understand what we did in the first part, we can go very fast over the second part, which is the isoparametric formulation. All right, so for the isoparametric formulation, remember that in general, we have some function in global coordinates. That function is a function of x, and we want to map this function to the natural coordinates domain. And the function here will be a function of some variable called psi. And to build this bridge, we're going to introduce a new term, which is the Jacobian. That Jacobian will contain all the information from the global to the natural. All right. Okay. So this graphical representation means that we need to substitute x in terms of the natural coordinate psi. That's pretty much what we need to do. If we achieve this goal, we can just go back to the formulation of the weak form for each element and make the corresponding substitutions. Okay? So the beauty of the isoparametric formulation is related with the fact that we can use the shape functions in all our expressions. So it means that if we take the shape functions in the natural coordinates, which is a function of psi, and the shape functions are defined in the natural coordinates as this. And its derivatives, their derivatives are just derivatives of each of them with respect to the natural coordinate psi. Let me do something here. So we have the shape functions in the natural coordinates and their derivatives as well. We can redefine some components of the weak form in order to reformulate our weak form in natural coordinates. So let's start for x. So we want x to be a function of psi, right? So if we do this, it means that each of the coordinates of the nodes multiplied by the corresponding shape function will produce the result we're looking for. Okay. So you see that this is pretty much the dot product between the vector containing the shape functions in natural coordinates and the corresponding location for each of the nodes in our element. That's pretty much what we need to do, right? So if our area is a function of x, so all we need to do is the substitution of that x in this form. All right. These xi, xk, and xj are just numbers, right? Are the locations in the x direction, in the x axis of each of the nodes I, k, and j. Okay. All right. The next thing we need to do is to define the Jacobian. So the Jacobian for an element is nothing else than the product between the location of each of the nodes in our element with the derivative of the shape functions. All right. So this is nothing else than the dot product between the vector containing the derivatives of the shape functions v bar and the vector containing the location of each of the nodes, xe, right? That's what it is. Another reformulation or definition in terms of psi that we need to do is the differential dx in the integral. So that would be just the Jacobian, the multiplication between, this derivative, this differential will be just the Jacobian and that with its multiplication with d psi. That's it. So since we already have this Jacobian, which is actually a number for our case, it's a number, what we need to multiply this Jacobian is by this this differential d psi. Next step is redefine our B matrix, B vectors. vectors. Remember that the v vectors in the first part of this problem contain the information of the derivatives of the shape functions with respect to x. But now we want these derivatives of the shape functions to be related, to be in the natural coordinates. So we're going to take this b bar and we're going to multiply the b bar by the inverse of the Jacobian to accomplish this. So I think we are done. Let's check it out. The weak form for the element was defined in the first part of this problem between the limits xi to xj. And it'll pretty much look like this. You can compare to what we did above. Okay, so in the natural coordinates, our limits are always range from -1 to 1. All our elements are defined under the same limits. So independent of the location of the element in the global domain. So it means that in our ref formulation, the integral now, we have the limits from -1 to 1. Our area, which is a function of x, will be now a function of psi. How? We take the equation for the area as a function of x and just make the substitution of x by this expression, all right? B, we have B transpose, but B transpose is just the transpose of B, right? So B, we already defined B. B is now B bar times the inverse of the Jacobian. And B transpose will be the transpose of B bar times the inverse of the Jacobian as well. The shape functions now are a function of psi. And they are given, right? They were given here in the previous step, in one of the previous steps. And the same substitutions apply for the right-hand side of the equation. So it means that now we have a formulation for the weak form in the natural domain, in natural coordinates. And all we need to do is to follow, to define this general formulation for the weak form for each of the elements, 1 and 2. The limits will be the same. The limits of integration will be the same because they are always from -1 to 1. And the Jacobian will be different. That's the only that will be different, right? Because it contains the information for each of the elements in the global domain. Okay, one more thing. I forgot, okay, I see that I forgot the perimeter here. So also the perimeter was as a function of x. Now the perimeter will be a function of psi. And, similar to the definition of the area, where x will be substituted by the corresponding expression above, where the shape functions multiply the x for each of the elements. Remember, x in xe, it's just the location of in the x coordinate of each of the nodes for each of the elements. All right. So it means that the perimeter and the area, when we define G1 for the first element, will be different from G2, right? So it means that this guy for G1, for the element 1, will contain information for the element 1, same as the perimeter. And for G2, it will contain information for the element 2. What is that information? It's just the location in the global coordinates of the nodes I, j, k. Okay? All right. So, okay, so I think with this, I finished I sketched what you need to do with the homework. And hopefully it will help you to finish and come up with your results. All right. So, okay, so that's all. If you have any question, please let me know and we will figure it out. Thank you and have a good day.